Hello everyone again. Let's keep talking pertaining to the Halliday and Resnick textbook, 10th edition, Halliday and Resnick textbook, 10th edition. This time we'll talk about chapter 28, magnetic fields. We're going to look at one problem from there, but there are other problems that are also available to you in the video. At the end of the video, they'll be scrolling through. In addition to this problem, available to you scrolling through at the end of the video, there will be other problems from chapter 28 scrolling through for you. This is generally the case for all of these chapters 22 through 32 that we're doing from the Halliday and Resnick book, 10th edition. At the end of each chapter, there are problems fully solved for you that scroll through at the end of the video, at the end of the film. They'll scroll through and they pertain to the particular chapter that we're working on. So simple as that. At the end of each film pertaining to a particular chapter, there are solutions scrolling through for you for that particular chapter. And that's been something we've been saying all along. Problem number 48 is the problem that we want to do. Let's talk about it. Let's see what we can say about it, and we'll kind of take it from there. For problem number 48, in chapter 28, pertaining to magnetic fields, problem number 48 says, a long rigid conductor lying along an x-axis carries a current of 5 amps in the negative x direction. A magnetic field, B vector, is present, given by B vector equals 3I hat plus 8x squared J hat with x in meters and B vector in milliteslas. Find in unit vector notation the force on a 2-meter segment of the conductor that lies between x equals 1 meter and x equals 3 meters. Okay. They did say milliteslas, so be careful here, guys. They said the B field's in milliteslas, so when you get an answer, you're probably going to get millinewtons. So then you got to figure out, okay, am I going to express this in newtons or leave it in millinewtons? That is about it. Let's take a look at some of the stuff that is available to us when we're doing this, and we'll take it from here. Well, we know a few things just down the road here. They told us. We've seen this on numerous occasions. If you've seen other films that I've tried to put together from other textbooks, they're the essential basic quantities under consideration that we're talking about are indeed found. I mean, anywhere you go. So let's see what we have here, guys. For some reason, I just want to make sure this is recording, guys. Okay, just not seeing myself on the screen there, but I'm assuming it's recording here. For problem number 48, we do know that F vector equals I L vector cross B vector. So with that in mind, DFB vector is going to be I L vector. Well, no, forgive me. If we're assuming that the I, look, this is kind of a subtle point in its own right, I guess you could say. If I and B vector do not change, but the length of the segment, along the length of the segment, there are differences. Forgive me, there's a lot to be said here, actually. B vector is a function. It is a varying function in this particular problem. The B field varies. B field's a varying function. L vector also varies if you're taking small partitions of the L vector, and we are doing that. I stays the same because they told us essentially it stays the same. They weren't telling us that it changed at all. So you got So we got this. Let's see what we can do here, guys. So we got this right here, and let's talk a little bit. Well, we got kind of in the back of our mind in the whole process here, we've got there's a few other things here I guess we could kind of say. They gave us B vector with an X component and a Y component. DL vector, it's going strictly in the X direction. It's looking something like that. So when you're going to actually do DL vector cross B vector, give myself a little more room here. We are essentially going dx I hat cross the following. bx I hat plus by j hat. Wrote them kind of up and down like this. I keep running out of room, given the way that I write you guys. So we have what we have here, guys. So there it is. I mean, if we're really going to find this thing out, kind of look at it, it's pretty straightforward stuff, actually, at this point. If it's looking like that, and that's what we got to do, well, I'll tell you what. I mean, I'm talking about, forgive me here, guys, this should have been DFB, force associated with the B field. It's a differential amount of force because we're talking about differential length as we're evaluating this. We have to talk about a differential length because we are moving along a line segment, but as we move along the line segment, the B field changes. If the B field is constantly changing as we move along a line segment of length capital L, as we move along that line segment, and the B field is constantly changing as we move along that line segment, we have to talk about differentials and get some kind of an integral because it's a constantly varying quantity that we're talking about. And that's obviously a problem that requires the mathematics of calculus to get it done. So you got this right here. So this is pretty important, guys. If you get to here, okay, we got that right there. Let's actually just do this. I mean, if that's the case, then FB vector is going to be the integral from 1 meter to 3 meters, x equals 1 to x equals 3. And now what's going on here? I mean, this is pretty important stuff. Well, you can say that when we talked about this right here, we talked about, again, they gave us, it could be anything, it could be a three-dimensional phenomenon. There's no z component associated to what they gave us, guys. So let me write this down again. We've got this. We said DL vector is dx I hat. Okay, we said all that. And if you were going to go like that, if you were going to go DL vector cross B vector, we're not worried about the I, you guys. The I is a constant. Let's do the cross product, we already got the constant as an I right there. Let's go dl vector across b vector is dx I hat cross, as we said, and there was only two components they gave us here, guys. The components they gave us when we're looking at this thing is b vector equals 3I hat plus 8x squared j hat. So, you know, the b vector is equal to 3I hat plus 8x squared j hat. That was something maybe we should have put in there. Now they're saying how this whole thing plays out. I mean, they're saying this, the I, it's going in the negative x direction, so it carries the current in the negative x direction. Well, we'll cross bridges as we need to cross them regarding that. Right now, let's just get a feel for what's happening here. You got the dxi, and then you got this thing right here, which is, you know, when you do the cross product here, there's a lot going on, but so let's, you got this. dxi, let's distribute it out. We know enough about the cross product, we can distribute it out if we do things correctly. Do the distribution, do it correctly. We know enough about the dot product. Forgive me, we know enough about the cross product that we can just distribute this whole thing out and we're fine. dxi hat cross bxi hat is 0. Or 0 vector. That's fine too, but it's 0 magnitude vector. dxi hat cross, so we know enough about the cross product. The distribution works with the cross product if we do things as we're supposed to do them, following the mathematics that we know, that we've already discussed. dxi hat cross bxi hat is 0 vector. dxi hat cross by j hat, I cross j is the k vector, and it becomes by dx k vector at the end of the day on that. That's pretty important stuff. Again, dxi hat cross bxi hat is 0 vector. dxi hat cross byj hat is the k vector. Is k vector, and that's, you know, at least as far as direction, and then it's just magnitude by dx. And we got that right here. That's pretty important. If that's the case, you are essentially, you know, you're essentially integrating this in the appropriate manner, and you know, and we know what that is. I mean, based on what we just said right here, guys, that's really the integral you're working on. Okay, well, let's figure it out. I mean, they just told us a lot here, man. I mean, this is your by, you know, also important. I mean, so you look at that as we look at this whole process. I mean, what is going on here? Well, just for the record, I think we know it anyway, but let's talk about it. 3I hat 8x squared j hat, the bx is the 3I hat in terms of magnitude. The magnitude of bx is 3I hat, or forgive me, Not that exactly, guys. Let me kind of think. BXI. Here's the BX I hat, and this is 3 I hat. So the BX is 3, the I hat is the I hat. BX I hat is 3I. BX I hat is 3I hat. BY J hat is 8x squared J hat. Okay. So if that's the case, at the end of it, what is going on here, guys? So you look at it and you say, okay, well, what this whole thing comes out to, when you actually ended up doing this, that right there, that was equal to this. And the BY was just this. The BY was the 8x squared. So what you're looking at is, it's I, and we'll kind of make our life easy. We'll say the I is 5 amps. I'll throw a negative somewhere. Might as well throw it here. Negative 5 8x squared dx. At the end of the day, that's going to be a k hat right here. And that's what we're doing, guys. That's essentially where it's going to go to actually get this thing done. So what do we got here, guys? Once again, I mean, you got FB vector is going to be k hat times the result of this integration. That's in meters. It's going in the opposite direction. Remember, the current is going in the opposite direction. It's not going from 1 meter to 3 meters. It's going from 3 meters to 1 meter. So somewhere in here, put a negative. You don't have to have the negative right here. You can have the negative right here at where the dx is, and it's a negative dx. Bring the negative out of there, and you're looking good. It doesn't matter where you're going to have the negative, but eventually account for the fact that there's a negative there. The force that's working here, guys, right? As we said, as the whole thing proceeds, where's it going? Yeah, bring that negative out. Bring it to here. Go the integral from 1 to 3. 5 times this, 5 times 8 is 40. You got this, dx. FB vector it's going to be whatever this is going to be now, guys, how we're actually going to get this thing done. So you look at it, and the integral here, by the power rule, is going to be 40 over 3, x to the, so what do we got here? We're going to have negative, running out of room here again, guys. Luckily, again, you have the feature. Negative k vector here, do the integral 40x squared, the integral of 40x squared dx is 40 over 3 x to the third evaluated between 1 and 3. Does Sounds good to me. Um, Three right here, x equals 3. 3 cubed is 27. Put 3 into 27, you got 9. 9 times 40 is 360. Put a 1 in here, that's just 1. That's 40 over 3. That's 13 and a third. That way, all of that K vector on that one, negative K vector rather, right? It's going to be, and we had the negative signs on there as well, right? Do the subtraction here, you're going to get 346 and 2/3. And that's going to be millinewtons. It depends how they want the answer given. I mean, that's what it is in it's millinewtons for FB, which is the same as negative negative 0.346, and the 6's go. Number of ways it can be done, but it's the same. And that's for the FB. It's as simple as that, guys. K hat. That means it goes in the negative z direction. Negative K hat direction is negative z direction. Okay, guys, so that's how that plays out. Thank you. We'll talk soon.